Welcome to the third in our Masters of Reliability webinar series. Today's topic, Forecasting Cable Faults at SRP, the Crow-AMSAA Reliability Growth Model. My name is Chrissy, and I'll be your moderator for today's session. If you have any questions at any time during the webinar, please feel free to enter them into the chat window, and we will address them at the end of the presentation. Joining us today is our expert guest speaker, Yancy Gill, Senior Principal Engineer at Salt River Project. Yancy holds a PhD in Materials Engineering from the Georgia Institute of Technology and is a registered professional engineer in the state of Georgia. His current work is directed towards reliability and life cycle cost analysis of transmission and distribution equipment, hardware, structures, and conductors. Prior to working in the electric utility industry, Dr. Gill worked for a major gas turbine engine manufacturer, estimating component lifetimes utilizing damage tolerance and probabilistic methods. Yancy, welcome, and I now turn the presentation over to you.
Thank you. I'd like to thank everybody for being here today and to Novinium for sponsoring this series. Today, I'd like to talk to everybody a little bit about how we go about fault modeling here at Salt River Project and managing our underground cable replacements and rejuvenation programs. First, I'd like to just give you a brief background into Salt River Project. We're a utility company located in the metropolitan Phoenix area, and we're primarily composed of two entities. The first entity is our Water Users Association. This side of our business was established as a private corporation under the Federal Reclamation Act. This is essentially where we got our start, and this all occurred in about 1905. The other part of our business is the electric side of our of everything, and that was formed by an agriculture improvement and power district, which is a subdivision of the state of Arizona. So, as you can see, we wear many hats here. We're an integrated utility in that we have generation, transmission, and distribution. So today we're going to talk a little bit about our underground cable. So if we look at what's on our system, what you're looking at here is some data from about 2012 or such. Our system's comprised mainly of number 2, 500, and 4/0 cable. The number 2 makes up about 2/3 of our footage amounts, direct buried. 500 and 4/0 make up about 1/3 of that direct buried. If we look over our faulting behavior, our 500, we typically see around 100 faults per year on that cable. On our 4/0, we're somewhere between normally 40 and 50 faults. And on our number 2, we're looking at faults in excess of 1,300 faults a year. So the challenge before SRP with underground cable is we have, at this time, roughly about 32.5 million feet of direct buried cable in the ground. It's primarily of cable that was installed from the late 60s up through 1992. One other date of note for us is all of our cable is jacketed except for number 2 cable prior to 1984. The last several years, SRP has spent in excess of $30 million a year replacing cable. And for that $30 million plus, we typically replace around 1 million feet a year. So you can see the challenge before us is we're expending, it's one of our highest budget items, 32 million feet in the ground, taking about 1 million feet out a year. So we've got about a 30-year program ahead of us. So the challenge is how do we manage cable replacement over a 30-year projected timeline? And the way we're going to do this, or the way we did this at SRP, is we developed some computer simulations that essentially mimic our cable replacement and rejuvenation processes. And we take the output from these simulations to give us some budgeting guidance. It helps us perhaps with some strategic replacements. and it allows us to monitor and evaluate our injection performance. First thing I'd like to talk about is data. Data is the foundation to this program. Without it, you can't do anything. The data that is of interest to us is primary cable vintage data, where the vintage refers to as the year of installation of the cable or the year of injection of that cable. So in terms of faults and footage, so that's the data we're after. Faults and footage based upon the year of installation or the year of injection for that particular piece of cable. Again, we take in, we're constantly updating our data, but annually we typically sit down and have a review to make sure that the data reflects the current state of the system and that we're staying on track with it, that we're not missing anything in regards to our collection of the data. Now I'd like to talk a little bit about the Crow-AMSAA model and why we chose this particular model to model cable faults. What you see on the screen now is the Crow-AMSAA model itself, and we use this both for cable replacement and rejuvenation simulations. The model looks at faults in terms of cumulative faults or cumulative faults per 100 cable mile versus cumulative time. And the lambda and the beta are basically the parameters that describe the fit of the equation to the data. We chose this model over a failure mode distribution such as a Weibull primarily because the Crow-AMSAA model models the reliability of a repairable system. A failure mode distribution models the reliability, if you will, of a replaceable system. The shortcomings with using that type of model on direct buried cable is two main shortcomings. One, with a failure mode distribution, it's only good for the first fault on that cable. Any subsequent faults, you end up again skewing the distribution. The other problem that you have with the model is defining the replacement unit. I've seen several people out there want to take a continuum of cable and just arbitrarily define it as a set length of like 1 foot, 2 foot, etc., whatever the length of the splice is perhaps. Again, you cannot do that with those type of models because you're changing the distribution. So with repairable systems, this a reliability growth type model, such as a Crow-AMSAA, is a preferred model. So if we take our data and we plot it, and we're going to plot it on log-log scale, what we'll find is if the model is going to be of value to us, that data will plot in a fairly linear fashion. Again, we're looking at cumulative faults per 100 cable mile or cumulative faults versus cumulative time. The slope of that line is the beta parameter in that model, your fault rate. The lambda is the intercept there at a log of 1. So what we'll do is let's take a look at an example here where we're going to look at some number 2 cable installed in 1980, and we're going to run it through the Crow-AMSAA model. So for our input data, what we have is we have our calendar years, faults, and footage. When we evaluate data for making a forecast, we look at the last 5 years of data because that best reflects the current state of the system. So what you're seeing there is for those calendar years, you see the faults and the footage associated with each of those years. So that's our input. Next, we'll look at the output once we run the model. Again, same calendar years, the cumulative time. Since we're looking at only the last 5 years of data, we start the clock at that last year, if you will, at 2008. We then calculate the faults per 100 cable mile based on each of those calendar years, and then again plot that up as you see in the lower left-hand corner, cumulative faults per 100 cable mile versus cumulative time. We then fit our modeling parameters to the data. We use two different methods of fitting the model to the data, a linear regression approach and a maximum likelihood estimate. When we do modeling, we use the maximum likelihood estimate because that typically gives us the best result, especially if we have some data that isn't as well behaved as some of the data as this piece of data you're looking at now. If you use the maximum likelihood estimate, you need to be aware of, for the Crow-AMSAA model, there are several formulations for that estimate, and we use the estimate based upon group data because that's how we're essentially analyzing our information. We're grouping all the faults and the footage annually, so that's how we analyze the data. Once we've run our Crow-AMSAA model, we can now forecast faults based upon cable replacement by reducing the cumulative faults per 100 cable mile to discrete faults. And then once we have the discrete faults per 100 cable mile, what we then do is multiply by the footage. So there's two examples here. The one on the left, we're going to replace 0 feet per year versus the one on the right, 50,000 feet per year. You can see the data with the blue diamonds. The model fit with the maroon squares, if you will, and then we have some confidence limits on there at 90%. And you can see the effect of replacing 50 foot a year. You can see how the faults end up trending in downward over the next 6 years. Since we're able to forecast faults based upon cable replacement at the individual vintage level, what we then did is we rolled all that up into modeling the cable replacement process with a simulation. So what we're going to do is we're going to look at cable, our primary cable, in terms of number 2, 4/0, and 500 over 30 years of cable replacement to see what, for a specific replacement scenario, what the faulting patterns look like. Here's an example of the input for the simulation. There's basically 3 parts to this input. We have our replacement footage, some cable parameters, and then our Crow-AMSAA parameters. Our cable replacement parameters, what you see here is, again, we're going to look out 30 years. So we have 30 years of replacement, and we can assign to each of those years how much footage we're going to replace. The data in the middle, this is some information that is pertinent to the cable type, be it number 2, 4/0, or 500. It gives us some information on customer impact, some cost information. There's some information in there as far as setting the clock, as far as our forecast. But the main thing to look at here is what is referred to as the beta bump. If you remember, beta is the slope of the cumulative faults per 100 cable mile versus cumulative time. That's our fault rate, if you will. So if we're looking out 30 years, we need to have a mechanism that will increase that slope, that fault rate, if you will, over those 30 years. And the way we do this is once the cable reaches 25 years of age, we randomly pick a number between the max and the min value you see here. In this case, it's 0.02 to 0.24, and we're going to add that to the current beta value. So what it's doing at 25 years of age, it's going to kick that beta value up a little bit. Going forward, it's going to do this at every 5-year increment. And we do this, again, to be conservative and to mimic that long-term reliability loss. And for each of these years, it's just randomly picking this increase. Sometimes it may be a little bit more, sometimes it may be a little bit less. Again, it's just a random pick from numbers from the max and the min value. The last piece of data is, again, all that Crow-AMSAA information that we previously discussed. You can see here we have our vintages of installation. We have our parameters, lambda and beta, that describe the faulting behavior. And then we have the last column is the footage, the actual in-ground footage. So when we run the simulation, the faults are determined via the Crow-AMSAA model. And then to assign the cable that's going to be replaced, what we do is we rank all the different vintages in terms of faults per 100 cable mile within the simulation. And we assign 100% of our cable replacement to the worst performing cable, which is that cable that has the highest faults per 100 cable mile. If we still have replacement footage left over, that footage balance is cascaded down to your second, your third, your fourth, your fifth worst performing cables until it's exhausted. And then we're going to run 30 simulations for each of those 30 years in the forecast, and we'll get some summary data in terms of median and maximum and minimum faults and customer impact. Next, let's just look at an example of running the simulation. And what we're going to do here is we're going to look at 4 scenarios. On the left-hand side of this plot here, you're going to see a column that has the total footage being replaced. So we're going to replace from 500,000 feet to 1.25 million feet. Out of that total footage, we're going to allocate to each of our cable types 50% to our number 2, 15% to our 4/0, 35% to our 500. And you can see those footage breakouts there on the right. So those are the simulations that we're going to run for each of our 3 primary cable types. So we run our simulation. We have the footage breakout for each type. Again, we have 500 in the upper left corner, 4/0 in the upper right corner, and then our number 2 result in the lower left corner. And what we look for is again, those long-term trends, and to see how that amount of footage replacement, and I guess I need to add here, this is done for all 30 years. These footage amounts are being replaced for all 30 years. So when we look at the data, or the output, what we find is for those lower replacement amounts, it's quite obvious with 4/0 and the number 2 that those amounts cannot sustain our system. The faults just continue to increase and really increase to the point to where we'd essentially have a system meltdown. The 500 is a little bit more interesting in that if we look at the faulting behavior and we were to pick the lower amount of cable replacement, that 175,000 feet, initially we'd probably think we're doing okay if we just want to maintain. We're maintaining and then we're slightly dropping. However, as you can look out into the future, you can see we'll reach a point where we have a lot of cable that's going to be coming of age and start to fault. And once that faulting picks up, that 175,000 feet cannot keep up with that cable. So again, from that standpoint, it's a replacement scenario that we would not favor. The flip side is when we look at replacing higher amounts of cable. If you look at, again, on our number 2, where we have 500,000 and 625,000 feet, same thing on our 500, our number 4. When we've replaced larger amounts of cable, you just don't see the bang for the buck as far as increasing those dollars and reducing faults. So again, we try to optimize our replacement by finding footages that maintain and slightly drive down our fault rates over the course of time. Once we do that, we look at what our customer effects would be. And in this example, the scenario is we're going to replace 1 million feet over 30 years with allocations that you see there, 50% for number 2, 15% on 4/0, and 35% for 500. And we see a max and a median customer impact. Again, what we like to see here is our customer impacts always being driven downward. And that's due primarily to the amount of footage that we can take out of our 500 and our 4/0 cable. That's primarily our feeder cable. So that's another a piece of the puzzle that we look at as far as setting replacement amounts. If you're modeling, you always want to close the loop on your model. You'll always want to make sure that the model is actually forecasting properly. It's forecasting historically. It will forecast the data that you've seen. And we've looked at a number of simulations. What you're seeing here is simulations from last year for us. 3 of them, if you will. We've ran several more. And the model fairly well matches up with our historic data. The 2 points that it doesn't is you'll see in about 2011 on our 500, we had about 145 faults. And on our 4-arc cable in 2007, we had about 75 faults on that one. And when we had those points, we always go back and reevaluate the model. And we reevaluate our data to make sure that we didn't mess up somewhere along the way, that the model's still continuing to describe the behavior. And when we looked at those 2 data points, what we found is they were primarily from letting jobs sit a little longer than we would have. We had jobs that were to be constructed, but we did not construct them due to land rights issues. So in trying to obtain land rights, the jobs sat a little longer. We had additional faulting on those jobs that drove our faults up during those years. The gratifying thing about this is, 1, it wasn't a modeling issue, and 2, it actually showed that our method of selecting those jobs to be worked was actually good, because these jobs were there, they were waiting to be released. We just had a few pieces of cable that we could not obtain land rights to. So in the process of sitting a little over a year, we ran into these issues. Next, I'd like to talk a little bit about cable rejuvenation. It's an integral part to our overall cable replacement process. And what we use rejuvenation for is we use it to mitigate faults on our number 2 cable, so we can put as much of our budget as possible on our 504-aught. To date, we've injected a little more than 8.8 million feet of direct buried number 2. When we look at our injected cable, we've got to answer 2 questions. And those questions are we actually getting fault reduction on our injected cable? And if we take that same amount of money and put it towards cable replacement, which is more economical? Is cable replacement more economical, or is cable injection more economical? I'll address the first question regarding fault reduction. Again, what we have here is a plot of our data in terms of cumulative faults versus cumulative time. We're going to use the Crow-AMSAA method again. However, on our injected cable, we only use cumulative faults. We do not use faults per 100 cable mile. And our vintage is the year of injection, not the year the cable was installed. So here's an example of a 2002 injected cable where we have, you can see the inflection point, and where we injected in 2002, the before faults versus the after faults from injection. And basically, you can see the slope of that line, that beta, if you will, decrease. So that tells us right there that, yes, cable injection is retarding faulting on this cable. The amount of faults it's saving us is essentially the difference between the 2 forecast lines there, the red forecast line on the before and the black on the after. So each year we can quantify the fault savings, if you will, from injection. So we know we're basically getting a bang for our buck with injection as far as retarding faults. Next thing we want to know is the economics. So to do this, again, we developed another computer simulation that, again, is going to mimic this injection process. We're going to pull in our Crow-AMSAA model to put a fault component on there, and then we're going to determine life cycle costs for replacement versus injection based upon equivalent uniform annual cost per cable foot. And here's how we go about that. If we take our injection budget, the choice is either we can inject it, use it for injection, or we can use it for cable replacement. If we use it for cable replacement, basically what we're going to do, we're going to calculate how much cable we can replace with that money. We're going to say that cable is going to last 30 years to the first fault. So that's got a 30-year life, fixed life of 30 years. We're then going to count our equivalent uniform annual cost divided by the footage replaced, and that's our equivalent uniform annual cost per foot for cable replacement. For injected cable, a little bit more difficult. What we'll do is we'll take our money and we'll see how much cable we can inject. And then using some of our historic injection information, such as how much successful footage versus unsuccessful, cable that we've had to abandon, etc., we're going to subtract off so much of that initial footage. We're going to take that footage, and what we're going to do is we're going to assign an economic life to that cable. So we're going to assign lives for anywhere from 2 years all the way up to 20 years and beyond. And we're going to evaluate the economic life of those individual years. And so what we'll do is we're going to take that cable footage that's still successful into this loop, and we're going to calculate how many faults are going to occur on that cable from our Crow-AMSAA, what our repair costs are going to be from that, how much warranty we're going to collect from that faulted cable. For every cable that faults, we're going to subtract out how much, a certain amount of footage from that cable, and it can vary anywhere from 0 to 100%. And then we're going to calculate a present value, then roll that up into an equivalent uniform annual cost, again, divide by that remaining viable footage, and then again compare that equivalent uniform annual cost per foot to the replacement. Example of the inputs that you'll see here, again, for a $5 million budget at 10%, you see our cable replacement inputs, our cost per foot. We have a salvage value, a life of 30 years. Our injection inputs, our cost for injection, a warranty and a repair cost, how much we're successfully injecting, how much warranty we would anticipate to collect, historically how much we typically replace of that cable, the segment length that we would be taking out per fault. In this case, we're looking at an economic life of 6 years. Again, we'll look at economic lives of 2 up to 20 and beyond years, but we're taking a snapshot per life cycle, if you will. And again, there's nothing magical about that. We, again, look at a variety of economic lives, if you will, when we evaluate our injected cable. And down below, we have our Crow-AMSAA fault parameters. Here's the outputs. You see the output on the far left for our cable replacement results. In the middle for our injection results, we have, again, how much footage we could possibly get for that dollar. We have our successful footage that comes out of all from the abandoned cable, the unsuccessful attempts up front to the faulted cable. So we're subtracting all that out. Our total number of faults, our repair costs, our warranty cost, and then we take that equivalent uniform annual cost divided by the footage. So for this scenario, an economic life of 6 years on our injected cable, it is more beneficial economically to inject cable than to replace it, because our uniform equivalent cost per foot are less for injection than for replacement. So when we run the model, we typically look at several scenarios, and you can see on the x-axis that economic life, injected cable life, versus the equivalent uniform annual cost per foot. For our replaced cable, that's constant over 30 years. So that's our black line. So now we're going to run 2 scenarios. We're going to look at our faulting in terms of using a beta of 1.2 and replacing 10% of that faulted cable, versus another scenario where slightly higher fault rate, 1.5, and we're going to replace now 25% of that cable. So as you can see, scenario A, we continue to decrease. We start to go asymptotic at about 20 years. Again, our break-even point is right around that. Typically we see break-evens a little greater than 4 and a little less than 6, depending on your how you move your parameters around, your interest rates. So our break-evens, we're just going to say, are around 5 years. But what we like to run the different scenarios for is mainly on the back end to see if we lose economic advantage. So what you see scenario B is if we start to experience these types of fault rates and we start to replace a greater amount of cable, we could run into a point in time where we become economically unfavorable. Currently, at SRP, we have 15 years of injection under our belt. So most of our cable is, a lot of it's between that 10 and 15-year mark or older cable. And scenario A best reflects what we're currently seeing for our injected cable. So I'd like to summarize everything right now. And again, we use the Crow-AMSAA model for direct buried cable because it models a repairable system and not a failure mode distribution of a replaceable system. It's a fairly flexible model. We can model faults or faults per 100 cable mile. If we use faults per 100 cable mile, then we can use forecast cable replacement in terms, or forecast faults in terms of cable replacement. Crow-AMSAA model, again, as you saw with our injected cable, it's great at evaluating the faulting behavior before and after injection. The really nice thing about it is it gives you that long-range view, and it allows you to manage over the long range and optimize your cable replacement over that long range, and your cable injection rejuvenation likewise. Again, the results clearly demonstrate what your budgeting necessities are, and if you have an asset management program, these type of modeling processes can be easily integrated into the strategic elements of your asset management plan. References, I've included a few references regarding the Crow-AMSAA. All of these are really good. So if you're interested, I encourage you to grab these and give them a look. So with that, I'll be glad to entertain questions. I have Rick Hudson here with me from our supervisor cable replacement. So I think between the two of us, we should be able to answer about anything that can be thrown at us. So I open the floor up.
Great. We have received some questions from our audience. So I will begin with, how did you choose a 6-year life for the injected cable?
That's an arbitrary life. Again, when we choose deals, those are economic lives. So, for example, we've got 15 years of experience here at SRP with injected cable. So we know out to 15 years basically how we're performing. So when we look at the modeling thereof, we look at those lower lives to determine our break-even point with replacement. So that's why we look at the 2, 4, 6, 8 type of lives. Then on the back end, we like to look at those longer lives where we're currently at and beyond to see if we, again, start to lose some economic favor over out at the long term. So the two things we're looking at is where's our initial break even, and do we lose economic advantage down the road?
Great, thank you. Our next question.
You're welcome.
Grouping by year means you are assuming homogeneous behavior for that year. How do you take into account bad spans that have multiple faults and or sides of open points subject to impulse?
Can you repeat that question, please?
Absolutely. Grouping by year means that you are assuming homogeneous behavior for that year. how do you take into account bad spans that have multiple faults and or sides of open points subject to impulse?
Okay. There's truth in that. When we look at that cable in terms of installation year, actually we desire that simply because that cable for that year of installation is typically the same type of cable, manufactured, geographically it's the same, and a number of things that are the similarity of that cable. So now when we look at that cable, typically what we find is we have vintages that perform much worse than others, and it's not chronologically driven per se. So yes, we roll up all the faulting for that vintage, and it's somewhat averaged out. To break it out in terms of segment, that is what Rick and his folks do. They've got a totally separate process where they're going to go in and they're going to look at number of faults on that cable, mean time between faults, and
reliability.
And the reliability of that
MBA
cable.
minutes out per failure.
So it's a kind of a two-pronged strategy. Basically what I'm doing is I'm trying to set an overall footage amount to maintain the system. Rick and his folks are very strategic in what they do and how they craft those jobs.
So we're looking at that yearly amount for these certain vintages, and then we are developing our jobs based on the worst performing cable with that vintage. So Yancy gives us a big picture look, and we then have to strategically decide, okay, how does that impact our system specifically? Where can we find these vintages, and where are these singular segments or singular areas that we're having the most failure activity? So yes, we see areas within that vintage that are much more poorly performing than others.
Great, thank you. Our next question, when prioritizing replacement, are you choosing the highest recurrence rate over the next couple of years or just the highest beta?
It's what Rick just said, and I'm going to let Rick address that. The only time that we will use the Crow-AMSAA model to target replacement has been on our 4-aught side, where our footages are much less than our 500 and our number 2 as far as vintage. So if we find we have some cable that's performing particularly bad, small amount of footage, then yes, that's telling us that pretty much as a whole, that cable's performing poorly, and we'll go out and maybe make some targeted replacements based upon the Crow-AMSAA method. From that, then I'm going to hand it back to Rick and talk about, again, how they pick that cable.
So again, with Yancy's modeling, we are able to get guidelines for what the next year's footages should be in terms of the different types of cable we have, number 2, 500, and 4-aught. And we just want to make sure that what we are scoping for cable replacement fits in with those percentages to get the desired outcome, and that is that hopefully we're turning the curve, that you're not seeing the growth that we see in failures that we've had in past history. We want to change that curve so it stays at the same reliability or goes down.
Okay, thank you. And our next question, our standards department has strong opinions about cable injection. How do you work with these guys?
Again, typically in the past, at SRP, we've had that issue come up. And I have to say, once we were able to demonstrate the fault reduction with the modeling, collecting that data, the data's key. Once you collect that data and model it and show everybody that, yeah, we are reducing faults, and then you put the economic element on it, typically everybody gets on board. Do you win over the hearts and minds of everybody? No. But what you do then happens is you don't have these prolonged debates of whether it is working or it's not. It's pretty much accepted that it is working, and you get more people on board with the program if you're able to demonstrate.
It took us about 5 years of a program before we could sit down with our standards group and get their buy-in that we were getting what we wanted. And that's really that model that Yancy showed in terms of the cable injection behavior over the long term. When you saw after 5 years that thing changing in terms of the number of failures going forward, that's when we're starting to get the result that we're looking for, which is while we don't move all of our failures to zero, we modify the amount of failures that we're having versus what we would have had. And that seemed to present to them the type of information they were looking for to give us the buy-in that we needed.
Great, thank you. Our next question, how do cable types, soil conditions, and cable manufacturers influence cable faults?
The only thing, again, that's one of the reasons why we look at installation vintage, is because typically within a given year, all those parameters are constant. The one thing that we can, again, as you would expect, our non-jacketed number 2 is our worst performer by far. We lose a lot of neutrals there, which increases the stress on the cable. We get deterioration of the outer semicon also on that cable. The other thing that we tend to find is, for those of us that are old enough and can remember some of the oil issues back in the 70s, we find some of various vintages of some of that 70s cable just did not hold up as well. So as we go through, we find that some vintages definitely perform worse than others. The thing you have to remember is every year as you're taking some of this poor performing cable out, you're essentially affecting the faulting behaviors of that vintage. And so every year, that's why we're constantly monitoring. We've had vintages at times where we've gone in, did our work for that year, come back the next year and modeled, and we've actually driven the faulting behavior to where the models tells us that we're not faulting, and actually our faults are reducing. Now physically, we know that doesn't happen. And so in the model, we always adjust the beta to be a 1, which is a random event in those cases. But in certain instances, if you have your cable replacement targeted right, and again, you're not dealing with substantial amounts in that vintage year, you can drive your fault rates down to a decreasing rate.
Thank you. And to follow up about neutrals, do you test the neutrals of the cables before injection?
Yes, all neutrals as part of our injection process are tested. And to date, from what our vendor tells us, we do not have as significant a neutral problem as maybe some other utilities are having. And that may just be a factor of we don't have a lot of moisture out here. It's a very dry climate. I don't know.
Is there a cutoff for when you won't inject because of deteriorated neutrals?
That is a decision by the vendor when they get there, and for the most part, my understanding is they have not had to apply a specific cutoff like many other utilities do in wetter climates.
A lot of time, if we get good flow through the cable, we will try to inject it.
Our next question, does SRP have SAIDI minute cost versus reliability benchmark?
A SAIDI minute cost versus reliability benchmark, no, we don't do anything like that. We have a group that takes the modeling data and then applies some SAIDI metrics to that data to give them a forecasted SAIDI, if you will. We do not do that on our end because, again, SAIDI is so much driven by the build of your system, your response time. There's so many things that go into that we do not model that. Everything's driven by the fault, and that's where we start.
We do on a job-by-job basis look at the MDA minutes that we had outage on to compare jobs in the cable replacement to sort of prioritize our cable replacement jobs for the coming year. So we have more jobs than we can actually physically do in any given year when we begin the year. And what we use that MDA minutes, which is a result of the failures and the actual reliability KVA, the connected KVA that was out of power, times the minutes that it was out of power, which is a numerator in that SAIDI component, and we use that as a factor in determining which jobs get greater priority on our job priority listing.
Thank you. Our next question, have you found greater cable failures at normally open points? If so, by percentage, how much? Do you install surge arresters at your normally open points?
We have not found a correlation to that. We've looked at it in the past. I don't know that we've done a recent analysis of that, but we did not find any specific correlation to the fact that a segment was near the normal open and it had more problematic failures. Now, the interesting thing, we have seen on longer segments, we see more failures on longer segments in a loop than the shorter ones. That's probably the only correlation we've ever found.
And I think we have time for one more question here. Does SRP inject any cable in conduit or any non-direct buried cable?
We did some CIC in the late 80s. That was cable and conduit, not installed in conduit, but it came as one package off the reel. And some of that, because we know we can't replace that, if we're beginning to see failures, and we've seen a very small number of failures in that, we have chosen to inject those cables at this time. And we are just starting to begin that era of cable in terms of our injection practices. So yes, we've just done a little bit of the CIC that we put in the late 80s before we went to all conduit in 93.
All right. Thank you so much, Yancy, and Rick as well, for helping us to answer those questions. And thank you for taking the time to speak with us today. Thanks to everyone for joining us. If we were unable to answer one of your questions today, we'll make sure to reach out to you one-on-one to address those questions with you. And we hope you enjoyed the webinar, and we look forward to our next Masters of Reliability webinar. Thank you.
Thank you. Thank you.